Alright guys, I'm back. So I told you I would do more flow videos, and we are going to do those. But I've got a lot of questions, and I want to make sure that you guys can trust what you're seeing out of my channel, the information that you're seeing, why it's accurate, and we're going to go into some of this. This is going to explain how the pitot tube process works, how the Orifice Plate process works, which is what an SF600 bench does, the theory behind both, how you calculate the CFM, all that. We're going to go through that. So this is kind of a nerd session. If you are into that and want to know more, keep listening. So hopefully this is educational. It's something a lot of people get wrong, and I want to make sure I explain the way this works. So without any further ado, the last video on the flow test you saw me use a pitot tube, which I talked about. A pitot tube measures, it's got a hole at the end, and that measures the stagnation pressure, total pressure, and then you have little holes around the perimeter of it, and those measure static pressure. Okay, stagnation pressure, static pressure. You take the stagnation pressure, subtract the static pressure, you get dynamic pressure. I explained that in my last video. So this is a pitot tube. Okay, we're going to talk about it first and how it works. So how to find CFM using a pitot tube. All right, some people see mathematical equations and start wanting to throw up in their mouth. This is real simple to understand. I'm going to go through it step by step. So a pitot tube, okay, it's used in Formula One racing, in aircrafts, in anything that needs to know airspeed, pipes, HVAC, they use them to measure airspeed. So it's all airspeed. If you know how fast the air is moving, okay, and you know how dense it is, okay, that's key, density. You can measure CFM if you know the diameter of the duct, okay? So what we're going to talk about is a horizontal duct, okay? No change in height, nothing like that, just a horizontal duct, which is how my bench works, okay? So P1 minus P2, the square root of that, which is your dynamic pressure. You take your stagnation pressure, subtract your static pressure, take the square root of that. You're going to multiply it by 4004.4, which is a constant. K factor, okay? The K factor, if you get a pitot tube from a manufacturer, that pitot tube has a K factor. This is a K factor of 1, which means I don't really need this term. I can take this term away and not use it. If you had a K factor of 0.8, 0.85, 0.9, okay, Dwyer, who makes a lot of these things and where this one came from, has different pitot tube designs, and each one has a different K factor. This one has a K factor of 1, so I do not need to change that. What I put here for either a pitot tube or the test pressure, okay? So for example, if I am measuring my flow at 28 inches of water column, which is how I do all of my tests, if I don't have a good enough bleed valve, like I have some of those issues that I got to work through, and when I test a valve, it's at 26 inches of water. If I turn another vacuum pump on, my bleed valve doesn't get it far enough down to 28. The closer you can get, the better, because this is not a perfect science. However, if you take the square root of the pressure you're wanting to test at by the pressure that you are testing at, you can get a K factor, or a correction factor, to get that flow at 28 inches of water. And I can explain that if somebody's got a comment on that or a question on that. Superflow has a board that you can look at, or you can just do it's simple math. You just take the square root of the test pressure that you want to be at by the test pressure you're at. It'll give you a multiplication. If it's greater, so if you're testing at 32 inches of water and you want flow at 28 inches of water, then it'll be less than 1. If you're flowing at 26 inches and you want to know what flow is at 28 inches, it'll be greater than 1. So As long as you did the calculation right, you will see that. If you put the 28 on the wrong side and divide the wrong side, you'll see that. And so that's your check. So K factor, it's either your pitot tube correction factor or your correction factor in inches of water. Okay. This is going to give you velocity in feet per minute. That's what this constant gets you. Okay. Feet per minute, which is what in the United States we're going to talk about, and I'm not going to get into empirical stuff. Okay. So this does not include corrections due to changes in temperature, changes in atmospheric pressure, or height. Okay. That's important. You need to, there's an adaptation to this that you can do to take those into account, but most people that are going to use a static pressure manometer can do the correction factor, and it's just look up Bernoulli's principle on compressive gases, and it'll tell you how to do that. There's a lot of calculators online. There's electronics, which I use an electronic. I use a Testo 510i. You put in the diameter of the duct, you put in, your air density for that day. Make sure you look at the barometer, what the temperature is in the room, not in the area, in where you're working, and take that temperature reading inside the duct when it's in pressure. Okay, I do that before I do anything, and that'll get you very close. Now, this math is very simple. The pitot tube is going to tell you this. So now, where this is important and where you can do this at home cheaply, go to the store, get you some plastic tube. Okay, you can put water in it with colored dye, Dwyer cells, the 0.825 or 8.82 something specific gravity red gauge oil. I recommend that. I've got that. That's what I use in my manometers. But you can use water if you're on a real tight budget. You can use water. And what you're going to do is you're going to do one of these two things. So, well, there's actually three. So you have a vertical U-tube manometer, you have a standard well type manometer, and you have an incline manometer. And there's differences, and scales change a little bit depending on which one you're using. If you use the 0.82 something specific gravity red gauge oil, remember you have to make sure that you're taking into account there's roughly a 20% or 10% increase in your scale length. I don't remember the math exactly, but you can look at that, and you just stretch your scale accordingly. And that's because it weighs less than water, so it takes a longer distance to reach 1 inch of water. So anyway, so what these are for is to measure this differential pressure. That's exactly what this is a differential pressure. Okay, same thing with the orifice. You are measuring the differential pressure between the tip of the pitot tube and those other holes, which is your static pressure, okay, and then your total pressure, and you're getting a differential pressure. So you take the square root of the differential pressure, okay, multiply by 4004.4 times whatever your correction factor is, if you have one, and that'll give you your velocity. Okay, so this is what we want to work on first. In order to get this factor, you need to use either a manometer or an electronic. I use an electronic, but you can use any of these. They're very simple to understand. The easiest to read, however, is an incline manometer. And this is where you just have to make sure that your scale is set up correctly. You got, in the way that, and a lot of people don't understand this, your flow, and I have it down here, okay, and incline manometers follow a logarithmic scale. The differential pressure across the orifice or across the tip of the pitot tube, okay, is to the square of the flow. Okay, now, and I just put in here that the inherent issues with the smaller versions is anything less than 60%. It's hard to see the small changes, and that's, if you ever see an SF600 bench incline manometer, you'll notice that the numbers are very, very, very tight, and they start to get further and further apart as you go down the scale. And that's because it follows that non-linear rule. Okay, So you can do this, but just remember, for every inch of water that you want to see, you got to make sure that your incline is only rising an inch, right? So if you want to be able to measure 10 inches of water differential pressure, you only want your vertical scale to raise 10 inches. Now, if you want it to raise 10 inches over a very far period, the further you make that scale 10 inches up, the longer you make it, the easier it's going to be to see those changes. Some people have 10-foot long manometers. You can definitely do that, and it makes it a lot easier to see those very minute changes. And you can probably do it all for 20 bucks worth of parts at Lowe's. Now, if you have a need for a smaller footprint, you can, and you have the budget, you can go get some of the blue gauge oil that they use in the SF600 benches, but it's like $150 for 4 ounces, so it's pretty expensive stuff. And it has a specific gravity of 1.9 something. It's almost a specific gravity of 2. But anyway, this is how you can get a percentage flow. Now, if you want a really tight budget, which most people are, you can do a YouTube manometer for about $5. Go get you some plastic tube, get you a 2x4, and you're just gonna raise and lower it, okay? If you're only wanting to measure this differential pressure, okay? Now, if you want to know your test pressure, you need just a regular well type or YouTube manometer. Works the same way. The only difference is, instead of putting your pressure taps going to each side of the manometer, your manometer, and I can show you on mine, but you only have it connected to the well side or one side of the manometer. The other manometer is venting to atmosphere, and depending on which side of it is depending on if you're testing intake or exhaust. If you're under suction, you're going to be on the top of the manometer because you're pulling the water up the manometer, okay? Or vice versa. If you use a YouTube manometer, it doesn't really matter what side you're on because you have a scale that measures both sides. So with a YouTube manometer, you have a 0 in the middle, and then it's 1, 2, 3, 4, 5, 6 going down and up. Okay, so if you want to measure up to 10 inches of water differential pressure, you would just need 5 inches in each direction. Now make sure your scale stops before it starts to U here. So this was a poor drawing on my part, but you want your scale to stop well before it starts to make that transition. And so the way this works is, if you're using a pitot tube and you have that pitot tube in the hole and you're measuring flow, the differential pressure is going to be much, 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 much lower than an orifice, okay? That is why a lot of people use the orifice style, okay? Now you can do this, but I recommend you make that really long, very slowly to rise manometer to get as close to accurate as possible. Because, for example, a cylinder head that flows 260 CFM, okay? If it flows 260 CFM at 28 inches of water, then you're probably only going to see something like 0.1, 0.11, 0.12, 0.13 differential pressure across the tips from your static and your total flow. So you're going to want that scale to be very large and only slightly rise. And if you're using a YouTube manometer, it's going to be really hard to see that change. So just remember that you can do it, but your accuracy is going to go down the smaller you make your scale. Okay, so moving on. If you have specific questions on how to do this for your application, let me know. It's just a matter of figuring it out. I recommend an electronic. If you can afford $100, go buy you a Testo 510i. Yes, they're not perfect, okay? Dwyer sells magnetelic gauges, and they work too. If you're flowing really small stuff like, lawnmower engine for some reason, if you're lawnmower racing and you're into that, motorcycles, you can get away with a very different setup than you can on an automotive car that's flowing up to 300, 400, 500 CFM on the intake valve. Now, that's how you get your velocity. That's step one. Step two is down here. Okay, step two is you're going to take your velocity in feet per minute. Okay, this is going to get you feet per minute. That's what this constant helps you with. And then what you're going to do is you're going to take your velocity, you're going to multiply by pi r squared. R is going to be the radius of the pipe in feet. In feet. This is where a lot of people screw this up. For example, my pipe is a 6-inch pipe. Okay, 6 inches is half of a foot. So this would be pi 0.5 squared, half a foot. Now, that is where this goes. Okay, you gotta remember that. If you're using an orifice, okay, an orifice is a little different because the orifice is even smaller. So I have a 3-inch orifice on my 6-inch pipe. So it would be pi, okay, and I've even got it here, for example, a 6-inch pipe has a radius of 0.5 feet. A 3-inch orifice has a radius of 0.25 feet. Okay, remember that. You want to keep it in feet conversions. It makes it simple. There's no more conversions you have to do, as you just do that as you go. This is going to give you your CFM. Now remember, this does not take into account temperature changes, density changes in the air. Okay, and I'll get into why that's important here in just a minute, but it's going to get you really, really close. Okay, if you're just wanting to see ballpark where you're at, this will get you there very quickly and consistently. So the next thing we're going to talk about, and I'll get back to the drawing over here, when we talk about orifice. An orifice plate is a very different setup. It's going to get you more consistent results because you can see much more minute changes. When you're using a pitot tube, you need to, one thing I need to add is when you're doing a pitot tube, flow, this is a cross section looking into the flow. Okay, you're going to want to measure at several different points. Okay, and then both vertical and horizontal, you're going to want to have this tested. Okay, so think of this as your pipe, and you're looking down in your pipe. When you pull that pitot tube, say I have this and the flow is coming towards the wall. When I do that traverse, you can do a time traverse, which is at a slow pace, okay, which is what I do. I do 10 seconds, very slow, perpendicular to the flow, and I do 10 of those, 10 seconds, 10 this way, 10 seconds, 90 degrees out from each other. There's a very, and then some people will recommend that you keep it here, take your test point, move it a little bit further back, move it a little bit further back, a little bit further back. It just takes longer to do that. They're both going to get you pretty good results. But you take whatever the machine tells you at those 10 seconds and you're going to average all of them together. And that'll give you your CFM. And I have literally got within 5 CFM accuracy out of this. So it's a cheap process. You can get a pitot tube for 100, 150 bucks, get the Testo 510 die for 100 bucks. And you're going to get really consistent results if you do it several times and average them together. Now, some people don't want to have to do that, which I changed my mind and I switched mine to an orifice style. And my next video is literally going to be me going over a flow test on my new bench. But before I got there, I wanted you to understand why I switched from this to this and how you use both and why what I'm teaching you has validity, that I understand what's going on here. So that's how you use a pitot tube, and you got to make sure that you understand how to use a pitot tube accurately to get accurate results. Now, orifice plate. Okay, now, an orifice, first off, I want to make sure I tell everybody you do not want an orifice to be larger than half of the diameter of your pipe. So I've got questions why I'm using such a big pipe on my flow bench, a 6-inch pipe. There's several reasons for that. The first main reason is the reason why you have to do these traverses is air's not laminar. It's just not. Okay, you can get flow straighteners, you can do all this, but it's not going to be laminar flow. If it was laminar flow, then you wouldn't have to do all these different test points. You could just throw the thing in the middle of the duct. You have full laminar flow, you're going to get a consistent result. Unfortunately, you may have 300 CFM down here and 20 CFM up here. It has to be the average. That's what's so important and what people mess up. Air in a pipe's turbulent. Okay, as soon as it goes down my bore plate, it has turbulence. It goes around that pipe elbow, that 90-degree elbow, even more turbulence. So turbulent flow, there's integrals. Like that is a highly calculus-based understanding to understand how turbulent flow works, how you measure it. The best thing we can do is get so many duct diameters away from that transition to get as close to laminar as possible before we do our tests. And we're going to be within a couple CFM, so it's not worth all the additional calculus involved. Now, how to find CFM on orifice. Okay, differential pressure across an orifice. We're going to go over here. This is a picture of a duct with an orifice plate. Okay, I have a 3-inch orifice plate and a 6-inch pipe. And like I said, it slows the air down on my I'm using such a big pipe because I need to be able to flow a 3-inch orifice to get to 350, 400 CFM of flow that I want to be able to measure to. The thing about that is the bigger the orifice, the smaller changes on the low flow spectrum that are hard to see on a manometer, and I'll explain why in just a second. And so that's your two reasons. One, it helps the air stabilize before it gets to the pitot tube or the orifice because the air is rapidly expanding. Okay, when rapidly expands, you're going to have a change in pressure, and that pressure is going to help slow down the airflow. Okay, the airflow is going to slow down, and it's going to be more consistent. So that's why I use a big pipe, and the other reason is because of the amount of flow that I want to be able to be capable of measuring. So the way the pipe is coming, we got this orifice plate here, and just assume the air is flowing. Say the bench is over here and it's sucking air, and the air is coming in this direction, and it's going to cross this orifice plate. When it does that, you're taking all that flow and you're bringing it to a tighter place. Okay, when you have that air changes and it's being forced to come through a smaller opening, you're going to have a change in pressure from this side to this side. That's what your probes are going to measure. Those probes are going to go to, for example, say you use a U-tube manometer. When it raises, you're going to have a differential pressure, so that pressure is going to go down on one side and up on the other side. What you're going to do is your scale is in the zeros in the middle, because you're going to measure 1, 2, 1, 2, 3, 5 inches of water differential pressure. That's the difference. Okay, the differential pressure is the difference in pressure between this side of the orifice and this side of the orifice. The differential pressure across the orifice is how you measure CFM. Okay, it's a very simple concept, but it confuses a lot of people. So I want to make sure you understand differential pressure is a big word, but all it means is the change. What is the pressure difference from this side to this side? Not what's the pressure on this side, not what's the pressure on this side. What is the difference? Okay, so if you're testing at 28 inches of water, that 28 inches of water is on the cylinder head, not the orifice. Okay, the orifice itself is going to have, 0 to 10 inches of water differential pressure. Now make sure you're measuring this in inches of water, which is what this is doing here. You can also use a well type. Don't recommend this. It's hard to see the small changes. The best of the best is an incline manometer. But again, I'm using a 3-inch orifice. So if you look at an SF600 bench, and I've shown this to you before, you have an orifice plate, okay? And those orifice plates have different scales, okay? Starting at a very small scale and moving up to larger and larger. 1.5 inch orifice, 3 inch orifice, 3.5 inch orifice, and a 4 inch orifice, or whatever the case. And each one of those is gonna have a specific flow characteristic, okay? So, that thing's a little dirty. Anyway, the reason why a SF600 bench uses different scales is because you want to see the flow between is 60% or greater. Because as I described, the scale gets larger and larger, so it's easier to see the small changes. If you're flowing a cylinder head on an SF600 bench at a 3 inch orifice, but you're only flowing at 200 or 300 thousandths lift, and it's only flowing 150 to 200 CFM, then you're going to want to be at the smaller scale, and it's going to have a higher differential pressure at that scale range, and that's going to get you down in here. So you may be flowing a cylinder head and you have 60% of flow at the 2.5 inch orifice scale, and then you may want to go up to a 3 inch scale as you get higher in your lift, and it's going to keep you in this 60 to 100% of the flow, okay? I recommend 60 to 80% of flow when I'm doing the tests. Now, I can get away with using a fixed orifice, okay, that goes all the way to my max flow potential, because I'm using electronics, and those electronics can see those very minute changes that we may not be able to see very good with our naked eye on a logarithmic scale, okay? And if that doesn't make sense, please send me a comment and I'll try to explain that a little bit better. It's easier to see in person, but just understand that it's a logarithmic scale. You want to keep it in the 70 to 80% flow. And I want to try and explain that one more time, because I get a lot of questions on it, because this is where people get confused. So, this is an orifice plate. This orifice plate flows 350 CFM at 9 inches differential pressure, okay? At 9 inches of water, okay? If I was flowing this on my bench and my bench did not have an orifice plate in it, and I floated at 9 inches of water depression, it would float 350 CFM. This is a sharp-edged orifice, which is what we're talking about. It can't be a rounded orifice because that equation's different, okay? So, pressure tap, differential pressure. It's as simple as that, the difference in pressure. That's all that is. So if that doesn't make sense, please get with me. But I think hopefully that will cover some people's questions. And the way that this formula works is how we're going to explain why it's important to know. Okay, so you have your differential pressure, and I'm going to show you this on my flow bench. So the next video we'll go into more detail with this, and I'll work out a few examples. But say you have your differential pressure here. This is the orifice test pressure range. So for example, what I just told you is your orifice. When you buy an orifice, okay, make sure you ask them what you can expect from it. So say at 9 inches of water, what does this orifice flow? And they'll tell you. So if it's a 3 inch orifice, it's going to be pretty close to 350 CFM at 9 inches of water on a sharp edge orifice. So because of the manufacturing deviation, you may ask for a 3 inch hole, but the laser cuts a 3.05 inch hole. You have to flow test it at 9 inches and see what the change is, because you might be plus or minus 10 CFM. You want to know plus or minus a couple CFMs makes a big difference in an engine, especially when you multiply it by 8 cylinders. So you want to make sure you get as accurate as possible. So this is where you're going to calibrate your bench, and I'll show how that works. But anyway, this is the test pressure that you're testing your orifice to. So for example, okay, and I do an example down here, but if My orifice flows 350 CFM at 9 inches of water. I'm going to take my differential pressure across the orifice and take the square root of that number divided by the 9 inches of water. Not the 28 inches of water I'm testing the cylinder head at. Because remember, the orifice and the cylinder head do not know that they're there. They don't care. One is seeing flow, one is seeing pressure change, okay? So if I'm testing my cylinder head at 28 inches of water, it's going to be the differential pressure divided by the orifice test pressure. Okay, for some reason my camera shut itself off. Okay, anyway, differential pressure across the orifice, the pressure range that you had your orifice calibrated at, the square root of that summation, or not summation, but you know, the division. You're going to multiply that by the orifice flow, okay? And this is the orifice flow you calibrated at. So if mine flows 350 CFM at 9 inches of water, we're going to take the differential pressure divided by that 9 inches of water, multiply it by the 350 CFM that I calibrated at. Boom, it's going to give you your flow, okay, in CFM. Now, considering this is a pressure change, okay, your negligible temperature change and your temperature change and all that is kind of negligible. The only time that this gets different is based off Bernoulli's principle, and Bernoulli's equation is change in elevation. There's a couple other things that you have to take into account. When you have a pressure differential, you're measuring at two different elevations. We're not doing that. So this formula is the simplified version of Bernoulli's principle, and it's just literally simplified to just the things we care about. And I designed my bench to make it this simple. I designed my bench in such a way to make it this simple so that I didn't have to worry about those other factors, keeping my math very simple and quick. So, all right, so that's just me explaining when you select an orifice plate, ask the manufacturer for the info, okay? Now, they told me 350 CFM at 9 inches of water. However, when I physically tested it on my tool, it was 375 at 9.01 inches of water. So, always test your equipment. And the reason for that, and I'll explain in mine, my vertical manometer at 9 inches of water flows 350 CFM, so the orifice is correct. My tool is off by 0.75 inches of water. I know that, so I put in the correction factor for that. You have to make sure you're calibrating your tool to the bench. Just because it flows 350 at 9 inches of water, if your tool is reading less than that, 8.25 inches of water, you're not going to have the correct flow. So you need to make sure if you're going to use an electronic device, it's calibrated to the bench, to the orifice, okay? So, and I'll show you how that works, or explain it to you in front of the bench. Now, examples. A pitot tube, differential pressure 0.14. Remember, differential pressure is going to be much lower than it is on an orifice, okay? Because you have on a pitot tube, the flow is not stopping. It is continuing on a differential pressure of an orifice. You have a buildup of pressure on one side of the orifice because you're taking all that area and you're cramming it into a smaller area. So when you do that, the volume doesn't change. The volume is still having to go through that smaller hole. So what happens? Okay, pressure reduces, speed goes up. Okay, now, which is an inverse relationship, something a lot of people get wrong, and I'll explain that now. And what we're going to do is take our K factor. Let's just assume we have a pitot tube that has a K factor of 0.85, okay, and your radius is 3 inches. Okay, let's just say you're using a 3-inch radius on this. Okay, density of the air will affect accuracy, so make sure you're taking that into account. But it's simple, using the formula, your differential pressure, square root of that, multiplied by 4004.4 times your K factor, gets you feet per minute. So let's say 1,274 feet per minute. 1,274 feet per minute, using your second formula here, you're going to multiply by pi r squared. If your radius is 3 inches, That's 0.25 feet. Pi times 0.25 feet squared, which is 1274 times 0.19635 equals 250 CFM. Okay, pretty simple. Same thing here, orifice plate. Differential pressure across the orifice is 4.35 inches of water. You can see how this and this is a lot easier to find than this. That's why this is used more. Okay, so your this is your next portion of the formula. Orifice test pressure, okay, your calibrated test pressure, and your flow that's calibrated, okay. This is using the specs from my bench, okay, using my tool. So the square root of the differential pressure across the orifice divided by your calibrated inches of water multiplied by the 375, which is the calibrated CFM, 261 CFM. So a lot of people think this is confusing, but just looking at these formulas, anybody can go, oh, I can do that. And that's what I'm hoping this video will help people understand, is building your own bench is easy. It's just a little time consuming to get the suction side done. The rest of it is a breeze. It takes no time. So I hope that this makes sense. We'll step away and I'm gonna traverse this just a little bit, just in case you're having a hard time seeing. That special note down there is very important if you're going to use that kind of scale. Okay, now if you have questions on anything you see on the board or anything that I covered, please ask, and I'll do my best to explain. Now, another thing people mess up, and I want to bring up in this video, supercharged applications, okay, nitrous applications, those kind of applications. One thing you have to remember, on the internet, do not listen to everything you hear, okay? And I know I'm part of that, but I'm hoping that this will prove some validity, that I understand what's going on and what I'm talking about. But what's important to understand is 1 cubic foot of air. Okay, we're measuring CFM, how many cubic feet of air per minute. Okay, 1 cubic foot of air does not change, okay, with speed. If you put positive pressure, pounds per square inch, positive atmosphere, okay, at 14.7 ambient pressure, additions to that, okay, boost, right? If you're increasing the amount of pressure inside the intake manifold plenum, that does not make more CFM. I want people to understand that, because it's super important, and people think that flow testing is not that important on a boosted application. You want to build your engine as naturally aspirated friendly as possible. The most power you can make naturally aspirated, because it's only going to be amplified with boost. Boost is a measure of restriction, okay? Just because you have 15 pounds of boost does not mean the same thing on several different applications. If I have 15 pounds of boost on one car, it could add 350 horsepower, who knows? If it's on another application, 15 pounds of boost on a stock 350 small block is only going to be worth like 80 horsepower, maybe a little more. And that's because of the CFM that the engine is breathing, okay? 1 cubic foot of air doesn't change. The only thing that changes with boost, when you cram the molecules closer together, you're increasing the oxygen content of that 1 cubic foot, okay? More oxygen means more fuel, more power, right? So more airflow doesn't make power, more fuel does. But the only way to burn that fuel in the right air-fuel ratio is to get the right oxygen level in this engine. So when you add boost, you're not forcing the air through the engine, okay? You're pushing the molecules closer together. You're adding more oxygen content. So ambient air, roughly 20% oxygen, okay? If you double atmospheric pressure, that does not necessarily mean you double the amount of oxygen in there. It supposedly does, but it doesn't always work that way. There's temperature and stuff involved. But like on a root supercharger, like what I have in Old Red, it's an air mover, okay? It's not a compressor. So when it moves the air, it creates heat. Their adiabatic efficiency is terrible, okay? And look up adiabatic efficiency, but the temperature rise. So as you cram more oxygen tighter in a smaller space to occupy a smaller space, okay, you're also increasing temperature. So temperature makes molecules want to move away from themselves, okay? But we're not wanting that. We want the air molecules to stay tightly close, all right? And that's why we mix more fuel and make more power. If temperature rise exceeds too much, then your efficiency of your supercharger is terrible and you actually lose density in your air. So that's why turbos and stuff use a cold air intake, and a intercooler is you want the air to be as cool as possible when it enters the compressor. Then you want to chill it back off before it goes into your intake. My supercharger doesn't do that. It's right on top of the engine, okay? So water methanol injection or E85 fuel is how roots blowers make just as much power as a turbo application. It's because the temperature, okay? Boost, no different. If you have 1 pound of boost on a supercharged application, 1 pound of boost on a turbo application, it's the same amount of pressure. The difference is temperature, and that changes the density of the air, which is how much power. 1 pound of boost on a car that has a turbo could add 20-ish horsepower. On the root style, 6 to 10 horsepower, depending on how much temperature rise. So it's how much oxygen you can cram into that 1 CFM. Now, the reason this is important to understand is people on the internet, you hear it all the time, oh, I don't need to worry about developing my intake manifold, or I don't need to worry about developing the intake port because I'm cramming the air in there. I'm just cramming it in there, so it's gonna all those sharp corners and terrible transitions and tight holes, it's just gonna go through all that. It's not gonna matter. Those people are gonna lose the race. Okay, the guy that built it to flow as much CFM as possible, average flow, and we're gonna talk about that. Your gross and net flow, we're gonna talk about that too. That guy's gonna win because 1 cubic foot of air, if you can flow 300 of those cubic foot per minute, and you just increased the amount of oxygen in that same 300, you're gonna make a lot of power. If you're the guy that has a 200 CFM amount of flow at peak lift, and you introduce additional oxygen by increasing atmospheric pressure and pushing those molecules closer together, you're not gonna increase your power. Okay, my camera overheated that time. Didn't know GoPros could overheat like that. I guess 4K might not have been the best. I was hoping the 4K would help see this a little bit easier. But anyway, just to make sure to recap that last little bit on a port, the more CFM you can flow, the CFM is not going to change if you increase atmosphere. You're only increasing the amount of oxygen in the same space, occupying that same cubic foot, okay? So develop your ports, keep flow testing, do porting, flow test some more, and get that port as optimal as possible at all the lift ranges. Keep your velocities high. All that is super important, okay? The boost is only going to increase the amount of oxygen content, and it's directly proportional to the temperature, okay? Mass airflow, okay? That's why you have mass airflow meters. The mass, the density of the air, okay? The density of the air is what's important, and that's what makes power, okay? Temperature moves molecules further apart. Colder temperatures move those molecules closer together, okay? So that's why turbos are better than root superchargers. Unless they have an intercooler, water methanol, or E85, and you're just normal 93 octane gas, that's why your boost limited and your knock limited, because your pre-ignition is gonna happen a lot easier because your temperature rise is so high. So that's what that means. That's why it's important. So keep flow testing, keep working on it. Hopefully this stuff makes sense, and I'll catch you in the next video. If you want to learn more of this, subscribe. That's it. Thanks, guys.